I would like to do a quick little video on factorial. Factorial is defined as an integer multiplied with all the smaller positive integers below it. We use an exclamation point to denote factorial. So, for instance, if we had 4 factorial, we would have 4 multiplied with all the smaller positive integers below it. 4 times 3 is 12, times 2 is 24, times 1 is 24. As a special case, we need to know what 0 factorial is. Please note that 0 factorial kind of breaks the rules that we just set. There are no smaller positive integers below 0. 0 is neither positive nor negative. But we are going to define 0 factorial to be 1. Let's look at a couple of quick examples. If we look at 8 factorial, we already looked at 4 factorial, so this one should not be too amazingly surprising to us. 8 times 7 times 6 times 5, 4, 3, 2, and 1. I always find the 1 to be a little bit of a nuisance more than anything else. As we take a look at, let's see, 4 times 3 is 12, times 2 is 24. 56 times 30 is 1,680. And 1,680 times 24 is 40,320. So there we go. A little less obvious, perhaps, is what we're going to do with n plus 2 factorial. With the n, we cannot get a numerical value, but I want you to understand that we are still going to multiply n plus 2 times the next integer smaller than it. Well, what's 1 less than n plus 2? It's quite literally n plus 2 minus 1. And what's 1 less than that? Well, that'd be n plus 2 minus 2. And what's 1 less than that? Well, it would be n plus 2 minus 3. And we would keep going with this process until we got to 3 and 2 and 1. So what are these values? Well, obviously, n plus 2 is there. If we took 1 less than n plus 2, would be at n plus 1. And after you do this a couple times, you start to see how this counts without having to write out, perhaps, or the minus 3 and the minus 2 and the minus 1. But we have, an n minus 1 at this point in time. You can see, although we don't have it written above, we would end up with an n minus 2 after that. And we would multiply by everything else until we got down to our 3 and our 2 and our 1, wherever they might occur. Like I said, we can't actually get values for this, but we might find in some places that knowing these particular terms, or these factors, I should say, could be useful. In the days of calculators, it's tempting to take a look at this problem and simply punch in 5 factorial on your calculator and 8 factorial on your calculator. When you do that, you get 120 divided by 40,320, which, as any calculator will quickly tell you, reduces to 1/336th. Now, that being said, I want to look at this problem a slightly different way. If we took our 5 factorial and we left it alone, meanwhile we thought about our 8 factorial, and our 8 factorial is an 8 times a 7 times a 6 times a 5, 4, 3, 2, 1. Well, a 5, 4, 3, 2, 1 is still a 5 factorial. So what we've created here now is something that will cancel off, and we are left with 1 over 8 times 7 times 6, which, as you can imagine, is 336. This particular problem shows the need for this ability a little bit more. If we look at n plus 1 factorial, that would be the same as an n plus 1. As we discovered, 1 less than n plus 1 is n. 1 less than n is n minus 1. Now, at any point in time, I can put my factorial back in place, and the rest of it will take care of itself. I choose to do this at the n minus 1 factorial because, just like we had with the last problem, with a 5 factorial on top and a 5 factorial on bottom, all the 5s would cancel, the 4s would cancel, the 3s would cancel, 2s would cancel. Here I have an n minus 1 that would cancel, an n minus 2 that would cancel, an n minus 3 that would cancel. Everything would cancel all the way down till that 4 and that 3 and that 2 and that 1. So these n minus 1 factorials can actually cancel since they represent a bunch of multiplication. And that leaves us with a simplified result of n plus 1, or n squared plus n, depending on whether you want it in factored or unfactored form. This is just a quick little help on factorial.